The first thing we've got here is a Sankey diagram. So a Sankey diagram is a representation of where the energy goes in a system. These can be very, very easy, and these can also be very, very complicated. So in the textbook, it has a Sankey diagram of the US energy production system. You can now get apps on your phone, especially if you've got like a solar and a battery system, and it can output Sankey diagrams to show you how your energy is being used, where the energy is coming from. In our example here, we've only got 100 joules worth of energy in, but that's from a single source. So if you were looking at multiple sources, you could have, let's say, a solar system and a battery system. You could output some energy to the grid, you could output some energy to a battery storage, you could then output some energy to your home. Sankey diagrams are a way of visually representing that system. So for the example that I've got here, I've got 100 joules worth of energy in. It could be from any range of situations. I've got, just for this example, 20 joules worth of energy going down, lost to friction, 40 joules lost to inefficiencies, 2 joules lost to the transmission, and that means that if we get our 100 joules, all our negatives, or what's being used out of the system, are going down. So 100 minus the 20 minus the 40 minus the 2 means that we actually get 38 joules worth of usable energy out of the system. This is just an example. I was possibly thinking about using 2 joules worth of energy used for bad jokes. The other component that we need to talk about before we move on to gases is energy density. So energy density is actually very useful in terms of monitoring the amount of energy that comes from materials or sources of energy, right? So when we're looking at this, we're looking at the joules per meter cubed. And this is given the symbol of ED. So our energy density is how many joules are available per meter cubed. Different materials are going to have a different energy density. So for example, if you want to have hydrogen, it is a very light material. Hydrogen has an energy density, so H2 has an energy density of 1.0 times 10 to the 7 joules meters to the minus 3. Uranium 235, it has an energy density of 1.3 times 10 to the 13 joules per meter cubed. So per meter cubed of uranium 235, you can get more energy out of it than you could hydrogen, which makes sense, mainly because hydrogen is very light and also it takes up a lot more space to get the same amount of energy out of it.